picking questions whenever sir permits us. We'll make you panelist. Otherwise, you can put it in your chat box also. We will read it. Thank you. Welcome, sir.
Okay, so very good evening. Hope am I audible, loud and clear? Can anyone say yes in the message chat box that I am audible? Oh, yes, yes. I think they're audible. All right. Very good. So I think we'll be focusing on fundamentals of. Can you just mute for some? Yeah. Mute, can you? All right. So and today we'll be talking about analytical modeling of energy storage devices. I am sure and confident that you might have gone through all the study materials during last couple of days. And to start with, let's get into different segments of energy storage devices. So we'll talk about a little bit of general model of energy storage. We'll move to different terminologies, mathematical modeling, battery degradation concept, capability curve, and evaluation of different battery modeling techniques, and finally, equivalent circuit models. All right. So this is how we normally model energy storage devices. Now, if you look into the complete concept, what we do, we connect the storage devices to the main grid, and the main grid energy is being drawn to either charge or discharge. So what we wanted to highlight that the storage device can act as a load or as a generator, and the moment it is acting as a load, then it is getting the energy from the grid. And then certainly, because we expect the grid is the variety of AC supply, then there is a conversion process from AC to DC, and the DC is available for my battery to charge. And depending upon the mode of operation, whether it is charging or discharging, the switch need to operate accordingly. And then idling losses is certainly some component representation. And finally, bit of charging discharge losses that do takes place in the series circuit. And then similarly, when I try to discharge the battery, so the battery energy is being consumed a little bit for the charging discharging losses. The rest is available for the grid to be charged. Then based on the state, the energy will be available in the form of DC. We convert it to AC and then connect to the main grid. So this is how the battery charging discharge normally happens. And it's a very, very basic model for your ESS, that is energy storage systems. So what are the main components of energy storage system? The medium through which the energy gets stored. Very important part is power conversion system, PCS, and then the balance of the plant, that is battery balance system, that is BOP. One thing all of you please try to understand, I will tell you some of my personal experiences and then I'll get into what is PCS. I was a bit fortunate enough to get a R&D grant to install 1 megawatt of battery in my laboratory in the campus. Very big, okay? So it is almost like 4 truck-sized batteries. This is the first of its kind. We were very nervous. So I got the grant, acknowledged DST for that. And they asked me how much money is needed. I said it is 2 CR because I Googled, I talked to many people, and the vendors told me, sir, 1 megawatt will charge you close to 2 CR. And I just approached the ministry also saying that actually I need 2 CR to deploy the first of its kind in the academic campus of 1 megawatt battery storage integration. I got the grant, I just floated the tender, and you all will be surprised to know the cost of 1 megawatt came to be close to 8 CR. That is almost 4 times of what I aspire. And then I was very nervous. I said I had a commitment to do something, but due to somewhere I went wrong. I don't know where I went wrong, but I asked for 2 CR. Whatever I asked, government has given to me. But now I'm not able to buy a battery of 1 megawatt. And you all will be surprised to know. Then I inquired with the vendor. I asked actually what is the cost of the battery, why it is 8 CR. In the past, many international vendors say it is 2 CR. Why you are asking for 8 CR? Then they said, no, sir, today it is 2 CR only, but the PCS, which is costing us more than double the cost of the battery. So what I wanted to highlight, the power conversion system and the control mechanism, and then the auxiliary services all together, okay, the whole mechanism, because lithium-ion battery stack is one thing, and the whole rest of the technology for conversion, charging, discharging, control mechanism, okay, everything all together become a battery. It is not about the lithium chemistry only serves as a battery. Battery means the whole concept is known as a battery concept. So 60 to 70% of the cost is not for the chemistry, but for the power electronics and technology. However, the battery chemistry cost is around 25 to 30% of the total cost of the battery that we see. So I do have a strong argument for you, all of you, those who are working in power engineering, and also my address to the nation in a sense that today we do not have lithium, but we can certainly create the rest of the technology that we are importing today, either from South Korea or from Taiwan or from China, wherever we do it, that is fine. But India can be independent in battery technology, at least to rest 75% of the technology for which we do not require any lithium or any chemistry for that. So by simply saying that we cannot be master of energy storage system is not true. We can be master of 75% of the energy storage system even today. Okay, so that is one kind of encouragement to all power engineers, those who are listening to my talk. Do something indigenous, at least to the technology attached to battery for operation. It is not, I do not want you to focus on chemistry of this because it has a long impact of manufacturing from a site, materials, okay, so many things. Country has really not moved so fast along with other countries. So the energy storage, certainly we are behind, but however, the technology, accessories technology to make this battery operational and to connect the grid, that's where we can contribute even today. So it is not enough to talk about power electronics simply, but we have to do it and show to the world that we can do it. Is it okay? So thank you very much. I'm moving to the next slide to understand a bit of terminologies. That is, what do you mean by ideal storage? Ideal storage is basically represent a very basic ideal lossless energy storage. Here I like to even talk to you a little bit about different type of sources. You all know what is a voltage source, you know what is a current source. But if some of you are teaching the course, I recommend strongly to also understand the practical, physical, lab-oriented current and voltage sources before you get into the energy storage sources, okay? This is also a DC source for us, no? When we draw a constant voltage source, we say that there is a battery, am I right, connected with a resistance and then the output terminal. So voltage source is nothing but which provides or supplies a constant voltage all the time. And the current source is something which provides constant current all the time, okay? So ideal voltage source is something similar to ideal storage or ideal battery. But in this case, we'll be representing the battery in a much complicated manner compared to the previous one. So storage, which is ideal, that our storage which is not true. efficiency is as low as 60 to 70% and as high as actually 85 to 90%. Now then there is one more cycle known as charging and discharging cycle and losses. So charging and discharging losses represent the charging and discharging losses associated with the conversion from the storage medium, example battery to electric energy and vice versa. Means if I charge a battery with X kilowatt, if I take it back, means it takes care of AC-DC conversion. If I give actually X megawatt of energy for my battery charge, if I take it back to the grid, probably that will not be my X megawatt. So it may be, let's say, 0.8X. So this 20% is the loss due to charging and discharging both. So that is what normally known as charging and discharging losses. Then we slowly move to inverters. It's basically a device. It allows dispatching reactive power, modeling the inverter losses, and limiting the rate of charge and discharge based on its rating. Inverter is a very common device for any batteries because considering the grid is AC and the battery is DC. We also define sometimes state that represent the state in which the storage element operate. The three possible states are either charging, discharging, or idling. Idling is one of the very, very severe state. Normally, none of us want to operate. I do not know how many of you are aware. If you use the battery and leave it idle, then your battery charging capacity will reduce by 5 to 10%. And probably it will degrade actually very, very seriously if you are not operating it nicely. And one more thing, actually very important part, all of you please remember, many times you realize that the laptop which you are operating on a regular basis, but if you do not allow you to come close to discharge completely, and then if you charge, probably the life of the battery is perfect. That means you allow it to discharge nicely, and at 10 to 15% of battery, you can again start charging. But what we people do normally, we use it at 85%, we put it in charging, make it 95, again use it, 86, again put it 94. So 70 to 95, we keep on playing, making your mobile always fully charged. That's not a good practice. So what we need to do, we need to allow the battery to discharge as close as possible, at least at 20% level. Somebody is messaging, hope everything is okay. I'm repeating, they are talking about actually idling. I'm coming there. So, so what I wanted to say, if you keep the battery ideal, neither charging or discharging, we'll slowly see the life of the battery will reduce drastically. All right. So any battery, if you do not use, so what exactly happens actually if you do not use the battery for a very long time? Because if it is a brand new battery, it is fine. But if you might have seen actually many times we keep a pencil battery even. If you use it will run for let's say 1 year for a clock. But if you don't use it will spoil in actually 25 to 30 days. Am I right? So that's why you can see there is a kind of a locking strip. So they say actually you pull it up once you feel like using it. So that means the moment you pull it up, it has to work. Okay, the cycle begins, the battery is continuously working, but keeping the battery ideal, that means you are not allowing the battery to get into the chemistry cycles of either charging or discharging. That slowly reduces the life of the battery to almost nil. What is idling losses? It's a very interesting thing. For example, if you have a transformer and which is not loaded, but still you experience some losses, all right? Similarly, if the battery is not in operation, still you experience some losses. Represents storage self-depletion losses and auxiliary loads. So it will try to dispose whatever the little energy it has continuously, and finally it will settle into a non-operational stage due to self-depletion losses. And we'll slowly move into the mathematical model part. I want your attention because this is very interesting. I'm happy that all these equations, though they do exist, but I request everyone to get into some of the good research publication by Tripta Tanwar. And I think she has done a wonderful job in optimal locations as well as energy storage. just try to explain the state of actually battery. Now, first of all, try to understand how the harmonic represents in a battery. I'm going a little slow here because you understand everything, because you can apply for the research in future also. DCH and EDCH is the charging and discharging power. Okay, if you have a battery, the amount of power you discharge, and we can also say the energy being charged and energy being discharged. But in these equations, we use power charging BCH and power discharging, it is BDCH. And then we have E rated, that is the rated energy capacity. The capacity is E rated, and E is the energy stored. Means the capacity could be 100, but stored is 80. Okay, so there are two different things. And then we are moving to UCH and UDCH. Is the state of the battery is a charging state or discharging state. The battery currently, I will say it is X, maybe that time of charging. I may say the state is Y when it is discharging, because the box is looking saying to me the battery is as usual. Okay, so we do not know what it is doing now. It is the state which will decide whether it is charging or discharging state. So when you formulate the equation, the energy stored at time t. So what is happening? It is 24 hours. It is 24 hours, and the charging and discharging takes place continuously. And you do not know what time charge and what time it discharge. So you need to give a command to the instantaneously. You say do this or that. So you need to design. Is the pre-operate. So everything is set, all right, okay? So before we do that, we need to know that the energy stored at time t, okay, at a given point of time, you have a scale, which is actually t equal to 1, 2, 3, 4, 5, 6, 7, up to 24. So any given time t, the energy is going to be E of t, all right? And I want to know what would be the energy of my battery at t plus 1 hour. That I do not know, right? So I have to predict now. So the energy at t plus 1 hour is the energy which was there before 1 hour, and then minus delta t times PDCH t upon eta. I'll explain all the terms, don't worry. Plus delta t PCH t multiplied by eta. The same thing, I mean, just open this minus sign, the minus delta t you take into the bracket. So you'll have the discharge cycle, which is represented as negative, and the charging has been represented as positive. So when the energy is at time t is Et, at t plus 1 hour, if you are charging, then Et plus whatever the energy being charged. Okay, and so now directly move to 1 hour. So there could be many other instances between 1 hour, between 60 minutes, maybe 5 minutes you charge, 5 minutes you discharge, 7 minutes you charge, 2 minutes you discharge. Many things can happen. Okay, that's what we have taken delta t. So there are multiple delta t's will, help me to understand what has happened in 1 hour time. Now the question is, all of you clear? For charging, it is positive. For discharge, it is negative. So charging added to E of t, discharge subtracted from E of t. But why we divide by eta and why we multiply by eta? That is a very, very important question. So whatever the amount PCH, what is power? What is energy? Tell me. Okay, rate of change of energy is power, am I right? So energy becomes power into time. So that's what we are saying, delta t times the power discharge, or delta t times power at the time of charging, the amount of power being received and become an element which is less than 1. Let's say it is operating with 90% efficiency. So then 0.9% of the P that you have obtained will be stored in my battery. But at the time of discharge, what happens actually? If I am interested to discharge PDCH, all right, so then probably I have to discharge more than PDCH to make PDCH available to the grid, okay? So that means if I say efficiency is 80%, so then 1.2 times of PDCH I have to discharge to make sure the battery truly had 1 times PDCH. So that is what actually the efficiency or the losses or the other reasons for charging and discharging losses is being taken care. So when you discharge, you divide by actually eta, and when you charge, you multiply by eta. All right. So that means what the battery will see within it during charging and during discharging.
This is power after the converter.
Yes. All right. So this is one equation I'm very sure that you all have understood. Now, one more thing, I cannot assume the battery can be at charging and discharging state, any given point of time. Because in the process of optimization, when you allow the simulation algorithm to carry out an optimization, it will make your things to happen whatever you love to have it. It is a mathematics there. It will take actually PDCH1, UCH1, okay. But honestly, the battery, when it is operating in charging mode, it cannot discharge and vice versa, okay. So to apply a constraint, not allow the battery to do simultaneous activity of charging and discharging, we have introduced a constraint that is UDCH plus UCH is less than or equal to 1. So these are the techniques I'm just helping you to understand. You can apply these methods to make sure that actually the battery is not getting charged and discharged simultaneously. So this logic, so what will happen, Manmohan? So the moment I say UDCH plus UCH is less than or equal to 1, so that means what will happen? Either this is 0, 1 or 1, 0, but or 0, 0, but it cannot be 1 and 1. So out of 4 states, okay, idling is charging 0, discharging 0, charging UCH1 and UDCH 0, discharging UDCH1 and UCH 0. Okay, but we cannot say both charging and so there is no state which is both charging and discharging. So this constraint we have introduced by making UDCH plus UCH is less than or equal to 1. I'm going a little slow to make sure that you all understand. All right. And then one more interesting fundamental of any battery operation. This is helpful for not only power system engineers, but also for power electronics engineers, because these are the states anyone has to forcefully accommodate in their algorithms. Now, the status of initial and final energy over a period of 24 hours. So when I wish to decide how the battery is going to operate in next one day, let's say today 5 o'clock to tomorrow 5 p.m. Okay. So in the process of optimizing, I have a wonderful battery which is fully packed, and next 5 o'clock I completely discharge, and I said I have wonderfully optimized my cycle charging discharging cycle. But the gentleman who will start working from tomorrow 5 p.m., he'll be given the battery with no energy. So first 2 hours will go only for charging, or first 4 hours will go only for charging to come to a zero state. So to maintain that, we also rest assured that the state of the battery of a complete 24-hour cycle must be at the same state. If it is fully charged, it must be left also fully charged. If it is 50% charged, it must be left with 50%. If it is zero charge, it will be left with 0. So the state at which we started, the state must end with the same state, okay? So then why we have not considered 100%? So because the moment you say 100%, there is a practical challenge. Dear students, please concentrate. The moment you say 100%, that means the next hour, T plus 1th hour, let's say 5 o'clock, it is 100% charged. So at 6 o'clock, I cannot charge anymore. All right, even there is excess renewable available to me, I cannot charge it because already fully charged. All right. And if I say, no, the battery can be charged up to 90%. And if the state is already 90%, then also I cannot do anything. So I must allow the battery to either charge or discharge even from the next hour itself. And to do so with a boundary of, let's say, 20% is the lowest energy state, 80% is the upper energy state. I start with 50%. So that next hour could be charging or discharging, depending upon my state, whatever I like to do it. And similarly, the ending point will be also at 50%. So two things I'm doing here, allowing the battery to immediately charge or discharge from the next state itself, as well as the state I have initiated my battery operation, I will leave the battery with the same state so that it is a true, because I'm not taking any extra energy from the battery or nor given any extra energy to the battery. And then the last component, which is depth of discharge. There are so many equations, but I thought I will not disturb you by teaching all those at this stage. So we are just teaching you the briefly. Probably I'll strongly recommend to read some of my old research articles published in multiple IEEE transactions, where already this information I have done it, but perhaps with one-to-one interaction, you understand more. And you can just go through. If you have any doubt, you can ask me at any given point of time. The depth of discharge, which is very, very important, it's a DOD, which is 1 minus E upon E rated. Now, let's say E is actually 80%, okay, and rated is going to be 1 per unit. So 1 minus 0.8 is 0.2, so that is nothing but 20%. So the depth of discharge means the amount of space available within the battery actually to get charged. Moving slowly to the next slide. There is a very interesting philosophy known as battery degradation. Why it is important? Because when you purchase a battery from the market, you will ask them actually what is the warranty of this battery or what is the guarantee of this battery. They will not say much about it. They will simply say the warranty and guarantee depends on the cycles that you have actually performed. So you may get the battery for, let's say, a period of 5 years. They assume that only you will charge and discharge once in a complete day. But now you are doing actually 100 times cycle, charging, discharging cycle in a day. So then certainly the life cannot be of 5 years. So it is maybe 6,000 cycles, 7,000 cycles, maybe 10,000 cycles. That is what is normally, and maybe 20,000 cycles, let's say. So that means if I do it once, then most likely for 5 years, the battery will operate. That is close to 20,000 cycles per week. Go ahead, tell me one more. Because 365 days, I will do, we consider charging, discharging 1 cycle. Per day, once if you do, then actually, how many years it will go? This is 400. 50 years. 50 years. 50 years. 50 years. You see almost all the commercial banks here. I have the guarantee for actually 6,000 cycles, 6,000 to 7,000 cycles. So they say almost like a 15 years. But I do not know. My batteries are actually only 7 years. heavy, but also not steadily also. So you should not be in the condition of idling, which is not good for health, all right? So calendar aging, which is battery aging, is a non-linear process. No one can guarantee that if it is a kind of a linear life cycle, it is not so like human being. It is completely non-linear. Battery aging is a non-linear process that depends on time, temperature, depth of discharge, and the number of charging and discharging cycle. If you read the complete charging discharging cycles of a battery, that's what you have been told not to charge up to 80%, not below 20% due to efficiency. However, am I audible? Dear students, am I audible? Yes, good, thank you. So similarly, actually, we can also look into the battery aging is because of the temperature, depth of discharge, and number of charging discharging cycle. However, the calendar aging, which is different, which is inherent degradation over time. The rate of degradation depends on temperature and SOC. So state of the charge is quite important, and the temperature is also equally important. So any battery storage technology, the efficiency of the battery depends on the temperature within which it is being protected. That's why all the truck size boxes having 300 to 400 kilowatt hour battery storage, we provide actually appropriate cooling to that, okay? So cycle aging, which is life lost each time the battery cycle between charging and discharging. So one cycle means there is a reasonable time we are losing on that, okay? The life of the battery depends on the times actually charge and discharge. So ESS, energy storage system lifetime, that is degradation per year, is nothing but the summation of number of cycles upon cycles after failure, and the lifetime of the battery is nothing but the reverse, the inverse of actually a degradation.
So even if it is discharge, let's say 100%, then discharge 10%, and again we put charge of it. One cycle we consider.
Yeah.
Or it has to be zero.
No, it is one cycle over, no. So that's what actually you have been advised not to do it. Now, if you, even your mobile phone, it is at, let's say, X state, which is 90% charge. I put charging, make it 91, okay, and take care. So one charging is over. Also, can you just lost your life? That is cycle aging, basically. That's what you have not been advised. Even we all wish to do that, but ignorantly we are, when you come out of the home, we say, charging, we keep on charging. And laptop also we do this blunder, we keep on charging. You should not do that. You charge it to 90%, take it out, allow it to discharge up to 15% or 10%, and then again you charge, you see the life will be minimum 10 to 15 years. Okay, some smart people actually do that, and most of us actually do not do that, all right? Now, moving slowly to the capability curve, this is also very anyone of you? No idea. Okay. So capability curve is about the PQ characteristic. Okay. I just explained in the form of a synchronous machine, and then slowly I can come back to your battery. So if there is a synchronous machine, what is the rating of a synchronous machine? Anyone of you can type in the chat box. How do you rate? What is the rating of a synchronous machine? How do you write? How do we do that? Can anyone of you say that what is the specification of an asynchronous machine? No idea? Okay, let's say it is being written as MVA. Okay, large synchronous machines are represented by MVA. They're not represented by megawatt or MVAR. Synchronous machines are represented by MVA, am I right? So when we say MVA, that means it is the apparent power, that is S. But it is keep on producing reasonable P and reasonable Q. But the mixture under root of P square plus Q square must be equal to S. Okay. When you say S equal to under root P square plus Q square, or S square equal to P square plus Q square, Anyways, that is nothing but a representation of a circle equation. Okay, so synchronous machine PQ characteristic if you plot, okay, the ideal one is simple a circle. Now, if S is fixed, let's say 100 MVA, and if I take 100 megawatt of real power, then my Q become 0. And if I allow the synchronous machine to generate 100 MVAR of reactive power, then my reactive power becomes 0. So that means when P is maximum, your Q is 0, and when Q is maximum, your P is 0. And from the circle, you can see it's circle equation, P square plus Q square equal to S square. When P is maximum, your Q is 0. When Q is maximum, your P is 0. Okay, that is how to actually PQ characteristic. So the capability curve, sometimes also known as PQ curve, and very funny way, it can also be named as a nose curve. Okay, as, I mean, you can. This looks like a semicircle, looks like a nose. So I think we'll try to the same philosophy is applicable to my battery, because as you all know, the battery can also provide reasonable reactive power, but most of the time it is reactive power. So if you consider that it can provide real and reactive because of inverter presence, and that case, we can operate it with a constant power factor, the left one. So what is happening? So constant power factor we have taken, let's say, which is minus 0.9 for an example. So you will get a straight line, which is your PQ characteristic with a constant power factor. However, if I like to plot a characteristic which is with different operating points with constant reactive power, the right one, if you see, the constant reactive power, so it means the real power is varying and the reactive power become constant. I can plot one more curve by saying that actually it is a constant real power, so then you'll have a vertical line where the real power is constant and the reactive power is keep on changing. So this is what the capability curve is all about. And why it is important? Why it is important? So when you decide how much power to be, energy to be stored in the battery based on charging discharging characteristic, means you are choosing a point within this circle, okay? So the operating point you have to choose. So if you put a dot in this PQ characteristic, that will decide how much P and how much Q that I want to generate out of it. All right. So and that will tell me, because different points will give me different P and Qs, and you have to decide how much P and how much Q you need at a given operating point. So this space is open to you, and you have to decide so that in a given period of 24 hours or maybe half a day, you can optimize your complete charging and discharging cycles. So moving to the next one, the battery modeling methods and their evaluations. There are so many models. The electrochemical model, merit is that it is high accuracy, no doubt about it, but the limitations are high computational power. The merit is balanced between accuracy and complexity, e.g. of online implementations, and the disadvantage is limited accuracy, and application is estimation of battery state energy management, grid-connected energy storage. So you can have different models with minor here and there changes. They're basically representative models. Then you can go for an empirical model where you can low complexity due to linearity else of easy of online implementations. However, the limitation is low accuracy, lack of insight of battery dynamics. And application is certainly grid-connected energy storage systems. We will now focus on a very, very basic equivalent circuit model, which is popularly known as PTC model, two-time constant representation of resistor capacitor ladder circuit model. So we can represent a battery even with many R and Cs, because that is how actually the battery is being represented. So you could see there is a voltage source represented by VOC, and then you have a R self-discharge, a shunt resistor, and then you have actually, a resistance RO in series, and then R1, C1 in shunt. and then Rn and Cl in shunt and become in series, and it's a continuous ladder network. Sometime we were thinking now why we haven't taught ladder network in our network theory, and probably they don't say the application there. They solve a numerical problem to you. You feel excited. You get 10 out of 10, but when you come to a battery study, you become 1 out of 10 because you don't understand the application, what has been taught in the past. So this is what the model is all about. Now we'll get into the details of TTC here. Our self-discharge is being a representation that denotes the self-discharge energy loss when batteries are stored for a long time. Just now I was telling why if the battery is kept ideal, then the battery life reduces and it is killed by itself, and that is being represented by a shunt one. Okay. So now tell me what is happening. I'll just explain you a little bit here. If you say the battery is non-operational, that means there is no load connected. The moment there is no load connected, no charging, discharging happening, so the battery become ideal. So there is no current flow takes place in RO here, am I right? So whatever the little current, because it's energy, okay, the battery cannot stop ideal. There's a reaction happening. There could be a lead acid, there could be a nickel cadmium, there could be lithium ions, a lot of action, and that action has to flow somewhere, okay, and that will really go through it, and then slowly the energy being dissipated, killed. So even though you are not drawing anything, but there is a cycle happening, and the life cycle reduces, and that is being represented through a shunt one. So our self-discharge denotes the self-discharge energy loss when batteries are stored for a very, very long time. The more RC circuits are used, the better the model can capture the transient of the battery, because it is basically a transient network, and because of transient, actually we represent the battery by RC networks. And many of you will agree with me that if I give you 230 DC and 230 AC source, and if I ask you which one is dangerous, many times people say, I will play with DC because I love batteries. It's not so, my dear friends. 230 volt DC is much more dangerous compared to 230 volt AC. The reason being, there is a transient associated with 230 DC. Okay. If you ask me what is the transient, again, I'll go a little bit into the subject here. You all must be knowing it, but still, let's say there is a RL circuit. Okay. If I plot the current characteristic, how does it go? V upon R into 1 minus e to power minus t upon tau. So the current will actually slowly keep on increasing. But if I say the resistance is not there, it's a pure inductor. So then my current become infinity, means it will spike and become an impulse. All right. So what I wanted to say, those kind of spikes only possible with your DC sources. All right. The AC source will never experience such kind of spikes. So that's why actually your DC supply is always dangerous, whether it is connected to resistance, reactance, capacitance, whatever you call so forth. So that's what actually the representation of the battery you can do wonderfully well by keeping as many as RC circuits in line. So, and whereas the open circuit voltage VOC is a dependent voltage source representing the open circuit voltage OCV, which is the battery terminal voltage after the battery is fully relaxed or released or nicely charged. R1 to Rn are the leakage or transient resistances, and C1 to Cn are dynamic capacitances. Even this is an equivalent model, but I will not say it's an exact, but you will close to exact if you keep those RC shunt circuit again and again up to n number of times. I just recommend all of you to read a couple of literatures, and there are a couple of people. I think the second and third reference become very, very important. You can see that's what I'm talking about. Trapti, Gangwar, and myself. In the reference 3 is certainly a very interesting one. IEEE transaction on industrial informatics, though it was prepared a long back, so I have mentioned early access, but now it's already there in public domain. You can just read it nicely. And perhaps the fourth reference is quite important. IEEE transition on Smart Grid 2022. And this article is also in the same time. So third and fourth, if you can refer, I think most of my talks you can understand much better. with this note, thank you very much for your kind attention. We are slowly moving further for optimal sizing and siting of storage devices. Now, once you understand about a battery, battery is fine, but how do you place? Okay, how do you decide for any system planning for distribution system? If you have to, because let's say I will give a battery to you for 100 kilowatt hour. What do you do with this? You will say, I will put it somewhere there. I will charge it, I will discharge it. Come on, do it. So in, let's say, MNIT campus, I have actually administrative building, I have electrical engineering department, I do have mechanical and civil engineering department, I have Acharya Bhavan as a residential area. So will I put it at X location or Y location or Z location, which is not known to me? That means the battery is fine, it is useful to me, but the location at which it will be placed, number one, and the magnitude of battery also need to be decided. For example, if I have a load of, let's say, X kilowatt, and if I have a battery of load actually X kilowatt, and if I do put a battery of actually 2X kilowatt, then probably it is not a proper sizing. So you need to understand what would be the size, means whether it is 50 kilowatt or 100 kilowatt or 1000 kilowatt, and the location A, B, C need to be decided properly. There are two challenges here. Why many people do research in this topic and why it is important? Because once the battery is being placed, replacement become very, very difficult. Replacement become very, very difficult. So just give me a All right, I'm back. Actually, hope you relax for a couple of minutes. Sorry for the interruption in between because I have to, make some necessary arrangement in between. All right, so we stopped at actually why it is important for sighting and sizing. So what exactly happens, because the batteries are very huge, and once you connect to a grid, normally we avoid replacing it. Similarly, So when you base it on capacity, but we normally don't change it, So once it is there, it's very difficult. So we consider a state, a given state with few capacitors in place, and then we decide what are the new capacitors to be placed based on the current load scenario. All right. Similarly, in case of battery, once you put a battery, it is very difficult to reduce its size. You cannot reduce it anymore. And neither you can change the location. Siting also you cannot change because it's a huge investment, okay? And hence, the first-hand experience, you have to be extremely careful because the cost of batteries are almost in the order of millions of rupees. So you have to be extremely careful before taking a decision. And hence, optimal sizing and siting of storage devices become an important topic. So what we'll do, we'll talk some certain important component, a general ESS allocation algorithm. We'll consider actually essential parameters. ESS integration means how it will be integrated to a distribution or transmission system. We'll focus mainly on distribution system. Then comparison of solution methods. Different methods we'll be comparing. And then we'll take a simple distribution network to test. I'll be very happy if you can simulate your own distribution network wherever you belongs to. But we have simulated a 33-bus distribution network, which is common and standard, available in public domain. Then I'll talk a little bit about problem formulation, input data parameters, and finally, the results. So today we'll be solving an interesting problem in next 30 minutes. So this is how actually, sorry that the letters are too small for most of you to read, but if you are using a laptop, probably it is easily readable. Okay. So general ESS allocation algorithm, what we say, a general distribution planning problem can be formulated as a traditional optimization problem. So it is basically optimization problem. Okay. It's a traditional objective function subject to equal and inequality constraint. That is what the basic nonlinear optimization problem look like. So what we need to do, first of all, the step number one is to identify the application to be served or necessary network support to be provided by an energy storage system. So you need to identify what is the energy storage system. That's what it's all about. So what we challenge, we have to stop. You can hear me, the student in the chat box. Can you hear me? Okay, great. So the video is a bit disturbed, but we'll continue with not it's okay. The student are writing some.
Internet issue.
Okay, all right. So good. So if you're audible, then we can go ahead with this. So, oh, not clear, not clear. There is disturbance, noise. Why it is so? The video is also not coming here, no? The video is also gone. Now it is okay. Great. Now it is okay. Now clear, sir. Very good. So much it is clear. All right. So first of all, you need to identify. First of all, you need to identify that goal to achieve energy is through ESS. So the step number one, let's say, I wish to reduce the distribution losses by putting a battery, for an example. Okay, so at the consumer end, instead of getting the power from the substation, I wish to have my own battery to make sure that the distribution losses are less. So that could be one of the objectives. One may say, no, I like to optimize the cost of the battery by appropriately putting the battery in a particular location. So you need to identify what is the objective for which you are aiming to put your battery. That means identify, step number one, the application to be served, necessary network support to be provided by the energy storage system that you need to identify. Once that is known, you can formulate the optimization problem to determine the size and location of ESS satisfying technical economic constraints. The input could be network information, ESS and its cost parameters, and the output will be optimal operation serving the chosen application. We will look into the detail of a problem slowly, but these are just ideas. And what would be my objective here? According to the network support, for example, minimize the investment, as I told you, and operation cost, minimize the power loss, and minimize the voltage deviation. So we can use the battery for power loss minimization. We can use the battery for voltage deviation minimization. We can put the battery for operation cost minimization. We can put the battery to defer the investment for a couple of years. So there are so many objectives one can design. And the constraints could be power flow constraint, ESS operation constraint, upper and lower bound on decision variables, and then you have to identify a suitable method to solve it. There are many methods, but some of them are mathematical optimization, classical optimization techniques, and probably you can also get into materialistic technique today, which are quite popular due to big data, and then analytical approach and AI techniques can also be used for optimal sizing and siting of batteries. Validation of the optimal size and placement result with test real power system network. That means you for PHIO and with a small rated battery, based on that location, you can burn the network into a simulator. And once you are satisfied, then you order the real battery and put it in the grid. So what are the essential parameters one has to know? And they are mainly technical parameters, and they are power flow constraints. For any distribution, you need to know what is distribution load flow. You need to know what is distribution optimal power flow. So you need to know what are the power flow constraints. You need to know power losses, what is renewable energy sources and load curtailments, energy storage system constraints and their capabilities, and finally, reverse power flow. These are all technical parameters and challenges. However, there are few economical parameters, that is investment or replacement cost or deferral cost, operation and maintenance cost, load curtailment cost, budget limitation, and then arbitrage benefit. One example I like to highlight here. The moment I say load curtailment cost means when there is energy shortage, what we do, we curtail the load. But we don't evaluate the cost of the curtailment. We don't evaluate the cost of the curtailment. We don't evaluate the cost of the curtailment. And through a battery, if you are reducing the curtailment, then you can compare how much cost we have to pay for a load curtailment and how that can be compensated with an investment for the battery. And finally, we come across actually environmental parameters, and they are actually emission level, resiliency, land availability, battery disposal, and recycling. So these are the main parameters. Now let us get into mathematical formulations, that energy storage system integration. One thing, all of you please try to understand, the optimal siting and sizing of battery is a completely non-linear and non-convex problem. It is completely non-linear and non-convex problem. We'll see how this can be solved slowly. So from the standard power flow equations, you might have studied in third year electrical sciences, power system 1 or 2 in BTech electrical engineering, the real and reactive power flow in any distribution or transmission system between two buses Pij is given by those two following equations. Now, because the battery is operational, the location will be represented by a binary variable, because if there are 10 locations you choose to be the priority, and if you like to put two batteries, so out of a string of 10 locations, either they could be zeros and one. So any given point of time, you will have two ones and rest eight are zero. So that is what actually we call binary variable for locations. And with integer, okay, so you can say it is 1 or 0 and the binary variable. And then once it is 1, you will have another string attached to that. It is about the magnitude, whether it is 1 per unit or 0.8 per unit or 0.4 per unit, that will be decided. So that will give you the size, and this integer will give you site. So distribution network planning, this is so mainly known as a distribution network planning problem. So when you put the battery, it is expected before the distribution network comes to action, like MNIT Jaipur campus is being built for the first time. That time I have to decide actually where to put the battery along with the distribution cables. But if you do it today, it is fine, but it's not a perfect planning because already distribution system is in place. And given the load condition, given the distribution network, now we'll optimize what would be the location. Am I right? So in IIT Roorkee, through our actually battery siting and sizing algorithm, we found actually 5 different locations where actually battery need to be installed. But due to sort of money, actually we could put 2 batteries in 2 different locations. Now rest 3 locations are still live. If the institute has money, they can put batteries in those 3 locations. I cannot put any more because I'm in Jaipur. So, and it can be solved using heuristic mathematical programming, analytical techniques, and AI, as we discussed. Now, there are many solution methods, details you can get into through different literatures. There are different methods. So we have analytical methods, mathematical optimization approach, AI method, and meta-heuristic approaches. There are a few limitations to everyone and then merits also. In case of analytical method, direct calculation lead to easy visualization, highly flexible, and the limitation is accuracy is low and slow convergence. In case of mathematical optimization approach, final solution guarantee global optimal, that is robust for linear programs, computational time dependence on problem dimension, explicit mathematical population required. Now, in case of AI technique, it is short convergence time, low computational burden, does not guarantee any optimal solution. That is the limitation. In case of meta-heuristic, it is easy, simple implementation, no gradient calculation needed, you get a solution. Then, but to avoid local optima, however, in case of disadvantage, it is high random, single algorithm can be trapped in local optimum very frequently because of its, for the non-convex function, you will have many local minimas, and anytime the solution based on the starting point, it will get trapped and exit, which is not acceptable in most of the cases. But if you ask me as a teacher, what is my choice, for a optimal sizing and siting algorithm, I will certainly recommend actually mathematical optimization approach, but no meta-heuristic, no AI, and no analytical methods. It is a classical method and it will work, but the times and certainly the computational time is an issue. But if you can have classical algorithms, probably you can address within 1 or 2 minutes of solution for a 100-bus system. So this is okay. So now we'll do a bit of analysis now. So case study, IEEE 33 bus distribution network. All of you please see there is a substation and there are 33 different buses. This is almost a research work. You can experiment at your home or even with your collaborators or guides or friends. Very simple problem. I will give you the case study. What I'm doing here, considering 33 bus, each and every bus has some load, could be a residence, could be a commercial complex. And we also put intentionally, that is the deviation we are going for, we put some locations with PV panels. We are putting some locations with PV panels. I will tell you why we are putting intentionally the PV panels. When I put the PV panels, that means the energy is not at all only limited to substation, but it is locally generating some power or energy through distributed generators. Now, PV penetration at buses 70. Consists of 33 buses and 32 lines and has a voltage of 12.66 kV and load size of actually 3.715 megawatt and 2.3 MVAR. So the total load size is 3.75 megawatt plus or 3.71 plus J 2.3 is the load. And we have generators, substation, as well as loads along with PV panels. Now, what exactly we want to highlight that is not being very clearly mentioned, we'll slowly see. So first of all, the approximations we have to consider before solving this network, because we like to put some battery there for our own goal. And what advantage it has not been, what is the goal has not been decided as of now. So first approximation one has to do for any distribution system before optimizing is nodal voltage magnitudes are assumed close to the rated voltage. Okay, so that is what actually we are assuming. And the second approximation also, we are saying that, theta ij equal to theta ji. And so that means the sine of theta equal to theta. That is what when it's very, very small theta, okay? And then your cos theta become 1. The moment you do that, then your linearized power flow, Pij and Qij between two buses is being defined this way. And then we can have a node power balance equation. This is slightly important. I will teach you how it is. So what you are saying, at any node, okay, you are having grid power, and then you have PV power, and then you have a battery discharge power, and then you have distributed generation, diesel generator power, okay, and which is almost the summation of all the resources be equal to the loads plus losses and injected and charging cycles. So when you create a particular bus, what it can happen, maximum what will happen, you will get some power from the grid, you will get some power from the PV panels. You may have a diesel generator that you do not know. You may have a battery, and that battery may be in charging operation or discharging operation. So everything need to be combined using the Kirchhoff's current law at a particular node. And that will do it for real power as well as reactive power. And the losses of the system can easily be calculated, and those equations need to be solved. In a power flow equation, we normally say there is a load and generation, but in case of a battery problem, there is a generator, okay, there is a renewable energy sources, and there is a battery. And you have to optimize the whole scenario to decide actually what would be the best location for my battery, as well as the size of the battery to be procured. Now, this is the equation we have already studied, actually these first three equations, and now moving to the objective function. So this is the battery constraints we already understood. The minimum sum power rating cost, what you are doing, the objective of this energy storage sizing will be to minimize the sum of the cost, that is the power rating cost, the energy rating cost, the fixed operation and maintenance cost of the lithium-ion battery, plus grid input cost. So what I'm basically doing, what is this objective, dear friends? It is basically the overall cost of the network I like to optimize. Okay, so indirectly what will happen? When there is a grid, I'm getting some power from the grid. But when I have a battery, that battery stores the renewable energy, for an example. Okay, so based on this operation, charging and discharging, the energy which is coming from the main grid is now also varying. This fellow is varying, charging, discharging. The grid energy which is coming is also keep on varying. So there is a cost associated at this point. For 24 hours, for the hour one, the cost is ₹1, the ₹2, ₹3, 7 p.m. it is ₹20. So there is a cost for energy at the substation. And this battery fellow is your own distribution network. So use this battery to charge and discharge in such a fashion so that the overall cost the distribution network has to pay will be minimum. All right. So this is what actually the objective function is all about. And there are many input data and parameters. So the parameters, there are many assumptions we made actually. They're not necessary to be exactly correct. So what we say, I'm going from the bottom to the top of the right side table. The DOD limit we assume to be 20%. Once again, and then the battery will charge for 4 hours. If it discharge, then it will discharge for 4 hours. That is the main objective. And then the capital recovery factor, that is 7% of lifetime of 10 years, which is close to 0.14. Assumed lifetime, which is 10 years. I think you said 15 years, I guess. So now it is 10 years. We have assumed this 10 years for practical one. Then fixed operation and maintenance cost, we assume 2% of the total cost. And then investment cost of lithium ion battery, because from NREL, we have taken the cost that is $370 per kilowatt hour. All right. So these are all reference based data. So because because you have to invest something, okay? If you are saving an electrical consumption bill in a year or in 10 years time, must be more than the investment that you made. Then only it is worth doing it. Otherwise, why do Manmohan will invest a lot of time in doing all these things, right? So, आप देखिए actually मनमोहन जी बाएं तरफ, this is actually we are talking about per unit load and time. These are the load characteristic, am I right? You will have different load characteristic. You may optimize your solution for a summer vacation or a summer duration, but which may not be true in winter. So we have taken all the load characteristic, the spring, the autumn, the summer and winter, because the battery remains there for whole 4 seasons. I cannot optimize for one characteristic. So you've taken round the characteristic, and then solar energy, which is available to me, that also being taken care, means at a given point of time, in a day, in a year, every day of a year, how the energy is available to me. So I have a irradiation pattern based on this PV energy is changing, and then I have a load, people are behaving differently. Then I have a source which the cost is keep on changing, and then the battery has to play dynamically so that overall cost become extremely very one of the most complicated problem one can come across in their life. It seems to be simple, but extremely difficult. And this, what I'm showing is almost output of, 3-year man-hour. All right. So it is, I'm talking in 20 minutes time. So no worry, but you please read it. I've given all the documents to me and my students, so you can refer and try to understand. So this is how actually we have also identified the voltage, because normally what we do in the process of optimizing, you try to violate all the limits of the network. You don't mind, okay? Voltage could be anything. I might like to optimize the cost, but the voltage is its own limit. So set states, we plotted the voltage characteristics of different buses, and we make sure that the violation is not more than 10% at any given point of time. And you could see the different bus number 17, 18, 32, and 33. The energy rating, you could see, I mean, the batteries, now we are slowly coming to a battery locations where energy rating of 2.78, 0.46, 4.0, 0.76, and the power rating is going to be 0.7, 0.121, and 0.19. So what we wanted to conclude, and I know the talk, the integration of renewable energy resources necessitates the allocation of distributed energy storage to mitigate voltage deviation, and deferred distribution upgrades. All right. And the method used here is mathematical programming, which provides a robust solution but may require significant computation time for large and complex problems. Uncertainty of loads and PV output and the life cycle of battery will affect the planning of battery energy storage system. This can be included in the problem too. Okay, many other constraints that we have not included, you people can include if you wish so. Also, the maximum discharging capacity of the battery gradually declines with its cycle, which can be kept as a future research direction. We are considering the battery's health on the day 1 is also same as the day 5 and day 20 and day 100, which is not true. The battery itself is a different battery. That we have not included in our analysis. With this note, thank you very much. I'm very happy that, we will be able to not only discuss on a subject matter which is purely theoretical, but we talked about, kind of more detail about mathematical understanding. With this note, now we are moving to the references, and then we will just have a look to those references, which are very standard. And once again, I will strongly recommend all of you to go through some of the references. And reference number 3 and 4 is quite interesting. And I would be happy if you can go through those papers and justify your understanding of today's lecture in solving a problem in near future. Thank you very much. Bye-bye. Oh, they're all very convinced today, actually.
So I think so. There is no questions.
I think it's good. I think so. I think it seems that they have understood very well today. If there would have been any question, but not limited today, even in future, if you have any doubt, actually, probably you can go through those equations and raise concerns. So I think once again, thank you very much for your wonderful attention. Take care. Bye-bye.
Thank you, sir. Thank you. So with this, we end our day 3, and we'll be meeting tomorrow. Sir. Just one.
Just wish to inform you that we have a very important activity tomorrow. But due to any reason, if there is any class movement or rescheduling, Dr. Manmohan will share you that information prior to the modification of any lecture schedule. Is it okay? One more?
Yes,
Fine?
yes, yes,
Thank
sir.
you. Sure.
So we'll let you know if any, as of now, it's 5 o'clock. I will inform you on WhatsApp
If there is
if there
any-
is any information or any change in the schedule.
Rescheduling of the lecture classes.
Thank you, thank you. Have a nice day. Thank you, sir.
Is number of time we place a battery in charge. I think some,
चार्ज साइकिल and the number of time.
ठीक है, what is asking?
क्वेश्चन पहले
Thank you, sir.
अच्छा उनको म्यूट करना है अभी सुप्रिया कुमारी पैनलिस्ट बनाना सुप्रिया कुमारी सुप्रिया SUP so charge cycle is the number of time
But the student is there?
in charge.
No, I think
I
Nikhil.
think that is the same question, sir.
No.
I asked the same question.
Okay, okay, take care. Thank you.
Thank you, sir. Thank you all.